So what are Bronsted acids and bases? Okay, so Bronsted acids and bases. Okay, so the key thing to understand of a Bronsted-Lowry acid is that it's able to donate a proton. Okay, donate protons. The bases, okay, accept protons. All right. Now the trick about this, you have to recognize which when it's appropriate that it can donate and when it's appropriate that it can accept. Okay. Perfect example, CH4. All right. This is neither a Bronsted-Lowry acid or a base. It's actually a neutral compound. And you're probably wondering, wait, but it has so many hydrogens attached to it. This ties in with the electronegativity aspect, okay? And also its electron number. We'll first discuss electronegativity. When you look at carbon and hydrogen, the electronegativity between them is 2.55 minus 2.20. These are 0.35, okay? And based on our limits of 0.4 and greater being polar covalent bonds, these are non-polar covalent bonds, okay? And with that being said, along with the electron number, okay, so CH4, all right, it looks like this with 8 electrons in total. If we did the math, okay, carbon, the electron number likes to have 4, and it doesn't have any lone pairs, but it's sharing 8 electrons with the surroundings. It's equal to 0. The carbon, and not just carbon, but when it comes to a lot of elements, they like to stay as close as they can to 0 for that electron number. They want to be able to match their I guess valence electrons with actually what they're working with in terms of like whether they're sharing and such. The hydrogen attached to it, okay, it'd be 1 minus, it doesn't have any by itself, and it's going to be 2 over 2 because it's sharing those 2, so it's also 0, okay? Now, with that being said, there are some things that are okay with breaking that rule to get bonds, okay? Perfect examples are NH3 and H2O, okay? These are examples of both technically Bronsted-Lowry acids and bases. H2O is one that's confusing me. NH3 is an example of a Bronsted-Lowry base because if you draw out its Lewis structure, it has 1 lone pair. This is a part that is perfectly fine accepting a proton. Now, although when it accepts a proton, the nitrogen becomes +1 for its electron number, to nitrogen, that is worth it because of the not necessarily the electronegativity, although that does play a part, but more specifically the hydrogen bonds. That's why it can kind of take or get rid of hydrogens, because the I guess gain it gets from getting a hydrogen bond, which is very strong, is worth the loss of losing, I guess, its neutral charge to become a positive charge. But you will never see, well, rarely, unless you really force it, you won't see NH2 by itself, NH2 minus. And in fact, it'd be NH2. Let me see here, because NH, because gain the hydrogen, take away. Yep, it'll be NH2 minus. Okay, you would really not see that because now it's lost a hydrogen bond and the nitrogen is at -1 for the electron number. That is like Why would it do that? It has now less of both sides. It's no longer stable, and it has less hydrogen bonds. Okay, water can work as a Bronsted-Lowry acid or base for kind of a similar reason. Okay, it has two lone pairs. All right, so with water, it can give away one of the hydrogens. Right now it says 0, and it's okay actually being OH minus, unlike the nitrogen, because hydroxide, it's like, you know what, I'm fine with this, strangely enough. Not really sure why, but that's what oxygen is okay with doing. But it can also use one of them and gain a proton there to become H3O. And kind of almost look like NH3. And this is where oxygen will be a plus. And this one is kind of similar reason, where it's like the joy of gaining a hydrogen bond cancels out the risk of, you know, of becoming a positive charge, of like losing its neutral balance. Okay, so that is what's happening there. So I guess the point of all this is to make sure that when you are seeing your molecules, make sure you're pinpointing which lone pair is okay with accepting a hydrogen. Okay, because you won't see this. Okay, this is too much. Although it has a hydrogen bond, okay, this is very unstable because now oxygen is at 2+. Okay, and it really, like at that point, it's like, yeah, I'm way too far from my neutral charge. So that's why this bond here would not serve as, you know, the Bronsted-Lowry base. And that's why you have to be really careful which lone pairs you pick. But on the flip side, you also have to be really careful about which hydrogen you're trying to give away. Like for example, in methane, those hydrogens are staying. You're not going to be able to like make carbon give away one of those. Okay, for ammonia, same thing. Those hydrogens are staying. If you had NH4+, okay, which is when this gained the hydrogen, this now can give away an acid. Okay, it's to go back to ammonia. This is ammonium, that NH4+, and then NH3 is ammonia. Okay, so that is just a tricky part of Bronsted-Lowrys and bases, is that you have to be able to identify which one actually can be given away and which space actually can receive a proton.